Welcome. This video will see how we identify maximum principal stresses in beams. We'll start with looking at this rectangular beam, and it's subject to a distributed load W. It's a cantilever supported at the farther end here, and we're looking at 5 points at different elevations. And these points are at the critical sections. If I look at it's a cantilever. Cantilever is at the critical section is at the support. And I'm looking at point 1, which is here at the top, point 5 at the bottom, point 3 at the neutral axis, and point 2 and 4 at quarter height at the top and the bottom of the neutral axis. So points 1 and 5 are the same in terms of the amount of stresses or the value of stresses that they feel. So from the shear point of view, because this is a distributed load, there is a V internal shear force developing, which is equal to W times L. But that shear force doesn't result in a shear stress at the top and the bottom of the beam because Q uppercase is equal to 0, so tau is equal to 0. And then the maximum normal stress will happen at the top and the bottom, which is equal to MC over I. And we'll call here, we used to call it sigma max, but in this case here, because we have principal stresses, which we'll call sigma max for tension, which is sigma 1, and compression, which is sigma 2 for Mohr circle. So here we'll refer to the maximum flexural normal stress as sigma m, which is equal to MC over I. So these are points 1 and 5. We'll have the same stresses and the top for this specific case, the top will be positive stress and the bottom will be negative stress. Point 3 is at the neutral axis. So now we will see a flip of the cases between shear and normal stress. So here at the neutral axis, sigma will equal to 0 because the y distance from the centroid is equal to 0. But tau is the maximum tau that's developing, tau m, which is VQM over IT. And for rectangular section we have seen in the previous video, it's equal to 3FV over 2A. Now points 2 and 4 are kind of in between. Like you will see stress developing, it's not large like tau m. Shear stress is not as large as tau m, and normal stress sigma is not as large as sigma m. So in that case, from point of transformation of stresses, these two shear and normal stresses can kind of combine forces and result in maximum normal stress at some orientation, which is the principal stress at this point. The question is, could the principal stress, which is we call here sigma max or sigma 1, at any point along the depth of the beam here, be greater than sigma m? So yes, sigma decreases with the depth over the depth of the beam. So the maximum happens at the extreme points, top and bottom. It decreases from here to the neutral axis, completely goes to 0. But while it decreases, also tau increases. So question is, while tau increases, now we will see in Mohr circle that sigma and tau would result in maximum principal stress. Would this maximum principal stress be more than the maximum flexural stress? So we will analyze here two sections, x at equal to 2c from here. So 2c, c is the point half of the height, and then x is equal to 8c. So we're analyzing two sections here, and we have the load here P, and if you check the textbook of the course, they kind of figure out the normal and shear stress as a function of P. And what they did is they analyze at different height of the section. So y here over c. So when y over c is equal to 0, that means it's y is equal to 0. And when the top point here, y is equal to plus c, then y over c, the ratio here is equal to 1 and then the lower point will be ratio, its ratio will be -1. And they figure out now the normal stress and shear stress at all these points. And what they did is they did a more circle analysis and principal stress analysis for all the points listed here to find the value of sigma max, or the positive principal stress, and sigma min, the negative principal stress, and find the ratio relative to sigma m, which is the maximum flexural stress that happens at this section. And what they found is, regardless of the 2 points, the 2 sections here, for any point along the depth of the beam, always sigma max, the principal stress of these points, will always be less than sigma m. And this is the case for both sections here, which means kind of we can conclude that in rectangular beams, the maximum principal stress in the beam will be equal to the bending stress at the top and the bottom fibers at the critical section where you have maximum moment. And that's kind of the conclusion of this table. And what they did also is kind of generalize this analysis and draw contours or lines here, what we call stress trajectories. And you can see here the solid line is the tensile, or what we call sigma 1, and the dotted line is the compressive principal stress, what you call sigma 2. And you can see here at the tip of the beam, m is equal to 0 and v is equal to p. And at the end here, this is a critical section, m is equal to p times L, the length of the beam. And you can see the trajectory, the direction or orientation of principal stresses at this point here, pretty close to 0. Like the principal stress is equal to, the ratio here 1, is equal to the maximum flexural stress sigma m. So sigma max and sigma m are the same. And this is the case here, and also the case here when you talk about compressive stress. But when we, excuse me, when we go farther away from the critical section, and we go farther or deeper in the beam away from the critical point of that point here, top and bottom, that's also the case here. The principal stress is the same as the maximum flexural stress. One thing to note here, at the neutral axis, the angle here that we see here, the difference between this angle here is always 90 degrees, because at this point the maximum or the principal stress, compression and tension, will be happening due to pure shear. There's no normal stress for moment at the neutral axis, but the pure maximum shear stress that develops at the neutral axis would transform into principal stresses sigma 1 and sigma 2, who are 90 degrees, away from, like, their orientation is 90 degrees away from each other. So in summary, you can say that in the beam you don't have to really worry about transforming stresses and principal stresses. Always, if for a rectangular beam, always your maximum stress that will govern the design of that beam will be equal to the flexural stress sigma m at the top and the bottom of the beam. It's not the case always like that in sections where there's sudden change in the cross section, and specifically here in wide flange sections. For these sections, you have to really think carefully that there might be a point where flexural stresses and shear stresses kind of get together and transform into principal stresses at a different orientation that would be larger than the flexural stress. In this case, principal stresses will be a concern. So let's see this wide flange and look at these points AB, which is the same as DE. And for point C is not really of interest to us because we're looking at the principal normal stresses, and at C there are zero normal stresses. There's only shear stress there. So if we go to check now this section, and let's say that it's subject to shear and moment, V and M, and we can say that there are two possible critical points that we have to analyze here and investigate if they have the maximum principal stress in that section. So point A, or also point E, and point B or point D. So we will analyze here, start with point A. So point A here, this normal stress is equal to sigma m, which is equal to mc over I, and tau is equal to 0. So if I draw the stress block, sigma x would equal to sigma m, and sigma y and tau xy will equal to 0. If I draw the Mohr circle, that's similar to what we found in the rectangular section. The principal stress at this point will be basically the same as the maximum normal or flexural stress sigma m. So there is no transformation of stresses, there is no, the orientation of the principal stresses is the same orientation that we have for this stress block. If we look at point B, y in this case will be less than C, so it's a little below point A. So we'll use here the formula negative my over I, and y here is not C, but it's pretty close to. So there's no big difference between sigma A, which is sigma m, and sigma B. But now tau would be pretty large. It's not 0, but if we cut just at the web, not at the flange, like we've learned about the shear stress development, tau B is pretty close to tau M, and tau M happens at the neutral axis. So it's kind of, we can also do some approximation here and say that tau B and the whole web here feels almost the same average shear stress, which will be equal to V over the area of the web. The area of the web is the whole web here is the full height times the thickness of the web. So D times T web. So I can say here that tau B, roughly by practice now, people just say it's equal to V over area web. So now these are the two stresses that are developing at point B. And this is the stress block. I have sigma x is equal to sigma B, and tau xy is equal to tau B. Sigma y is equal to 0. So if I draw this, the Mohr circle for this stress block to be a diameter for that circle, and if I look now, I'm not at the orientation of principal stresses, so I have to have a 2 theta p orientation in the circle, or theta p in real life. And in this case here, that's actually should be theta principals. So that one here is theta p. So you will find that theta 1b, or theta maximum of b, the tension, is equal to the square root, so it's equal to r. So that radius here is r, and this r I can figure out from this triangle here. Is equal to the square root of theta b over 2 squared plus tau b squared. And now this theta b1 or theta 1b will be larger than theta x that I would just, if I focus on flexural stresses, then it will not be the critical value. Actually, the transformed value of it with tau will be the principal stress. This is the maximum at b. Now, if you think about the whole section now, the whole cross section, I will say now the maximum normal stress in the whole section will be the maximum of the principal stresses that develop at point A and point B. And depending on the values of V and M, in sections where they have the sections that have large V relative to M, point B will be critical because the principal stress here will be magnified because of tau. But in typical sections, usually normals, the moment results in flexure stresses that are more than, in terms of magnitude, shear stresses. So typically the top and bottom points still govern, but still you have to do that analysis. You have to compare between principal stresses at these 2 points, the extreme top or bottom point, and then the junction point between the web and flange. So that's it for this lesson. It's exposing us to a very interesting concept here, that we are now designing beams based on principal stresses, not based on normal flexural stress that happen at the top and the bottom of the beam. We are really careful about picking which point now, especially in beams that have change in cross and the thickness of this, the cross section, like wide flange or C sections or standard sections. For rectangular sections, you don't have to worry. You just do what we used to do before. Maximum normal stress will be equal to the flexure stress at the top and the bottom of the beam. All right, so that's it for this video. And the next video we'll learn about, we'll see an example of that in numbers, and we'll see what's really the case. Will point A govern, the top of the flange will govern, or the junction of the web and flange will govern? So stay tuned. I'll see you in this video, other video. Take care of yourself and your family.